In this problem, we're going to take a look at an application of the chain rule, and one that's going to require multiple chains. So the voltage across a circuit is given by Ohm's law, which states that voltage is equal to current times resistance. If we place two circuits with resistance R1 and R2 in parallel, then their combined resistance R is given by 1 over R equals 1 over R1 plus 1 over R2. So if you're not familiar with circuits, imagine that we have imagine that these are wires connecting two components. And we have some sort of battery over here, and we'll just write the battery as, this could be positive and negative, and we have two resistors here. So a resistor could be anything like a light bulb, it could be some sort of device, it could be a resistor on its own, and this resistor has resistance R1 and R2. So this is what we call putting two resistors in parallel. So it's typically on Christmas lights or holiday lights, they're strung together in parallel so that if one bulb goes out, the whole string doesn't go out. So that's really one of the common applications of connecting things in parallel. So we have all these relationships, and what we want to find, we're told that the current is 2 amps. Okay, well, let me write down a few things here. So we know that the current is currently 2 amps. We also know that the current is increasing at 10 to the negative seconds amps per second. So that means that di dt, the change in current per second, is 10 to the negative 2, which is actually 0.1. So 0.1 amps per 1 second. We also know that R1 is 3 ohms. So R1 is 3 ohms, and here's the symbol for ohms. We know that R1 is increasing at 0.5 ohms per second, so that tells me that dR1 dt equals 0.5 ohms per 1 second. We also know that R2 is 5 ohms, and it is increasing at a rate of 0.1 ohms per second. And what we want to do is we want to calculate the rate at which the voltage is changing. So in other words, we want to know what is dV dt when all of these conditions hold. So when we have basically all of these things to calculate it with. So let's start off with the chain of events here, the chain of things we know. So we have voltage, and voltage is a function of two things. It's a function of your current, and it's a function of your resistance. Now, the only relationship that we know about I is that I is related to time, that the current is going to be changing with respect to time. So here I'm going to put a t variable, and I know that I depends on time. I know that R, even though this is not solved for in terms of R, it's 1 over R, but I know that R is related to two components, R1 and R2. It's going to depend on what those two individual resistor values are. But R1 is changing over time, and R2 is changing over time. So this is how our chain looks. Again, voltage at the end of the day is going to be a function of time. But in order to get it to be a function of time, I have to consider its relationship to current and its relationship to resistance. If I start to build out these chains, I see that this is going to be dV di, and this is going to be dV dr. I'm using partial notation because V depends on two inputs. I depends on t, so there will be a rate for di dt. R is going to depend on R1, and R1 is going to depend on time. So let me start down here and say this is dR1 dt, and this is going to be dR2 dt. Not using the partial notation because all three of these variables, I, R1, and R2, are directly the function of just time. Now I'll also have two other derivatives here. I'll have, now since capital R, the total resistance depends on the individual resistors, I'll have dr, dr1, and I'll have dr, dr2. Now I'm going to actually label some of these components because I know what some of these are in my instant. I don't necessarily need to know what the function I of t is, because at the current moment, we know that that's equal to 0.1. So here we're given that piece of information, and we can say that this is equal to 0.1. We also know that dr1 dt is 0.5 ohms. So this is going to be right here equal to 0.5. dr2 dt is 0.1. So let's highlight that in a different color here. Let's go with some blue. And we know that that value is 0.1. So what we don't have values of are dr, dr1, and dr, dr2. So I'm going to need to get this because as you're noticing, in order to get the dV dt, I'm going to have to get the contribution to the change in voltage due to the change in current, as well as due to the change in resistance. So I'm going to have basically three terms. I'm going to have dV di times di dt. That will give me dV dt. I'll have dV dr times dr d1, dr dr1 times dr1 dt. I know it sounds like a lot, but let's go ahead and write this out and see what we actually will need to compute. So to get dV dt, I have my first chain, and I'm going to have to take dV di times di dt. So we're going to write dV di times di dt. We'll see that the di's cancel, and we're left with dV dt. So you can think about this as the, I'll write it down here, this is the current effect. And then I'm going to add to that the resistance effect. But there's going to be two different resistance effects because dV dr times dr dr1 times dr1 dt, if I look at the units of those and how those cancel out, you'll see that that will be dV dt as well. So dV dr times dr dr1 times dr1 dt. And again, if we follow the cancellations here, the dr's cancel, the dr1's cancel, and we're left with dV dt. So we can call this the resistor 1 effect. To that, we're going to have to add the remaining component, which you might be seeing by now as dV dr times dr dr2 times dr2 dt. So I'll have plus dV dr times dr dr2 times dr2 dt. And this right here is the resistor 2 effect. So once again, our units cancel, the dr's cancel, the dr2's cancel, and that again gives me dV dt. To put this all together, we have four partial derivatives that we need to calculate. So we need to get the values of dV di, we need that guy. We need dV dr. We need dr dr1 and dr dr2. All of the other ones are known. So we're going to be able to replace di dt with 0.1 and dr1 dt and dr2 dt with their respective numbers. So we know that V equals IR, that's how voltage is related to current and resistance. So to get dV dy, I have to take the derivative of this with respect to I, which will just give me R. Again, you could go to Wolfram Alpha, type in d/di of I times R, and you should get this. dV dr is going to be I, for the same reason. In this case, we could factor out I because it would be constant, and the derivative of R with respect to R is 1, just like the derivative of X with respect to X is 1. Now I know that 1 over R is equal to 1 over R1 plus 1 over R2. To take the derivative of this, we've got to be cautious because this equation is 1 over R equals, not R equals. So if I take the reciprocal of both sides to make this easier on myself, I'll have R over 1, so take the reciprocal of the left side. Think about this whole thing as being over 1 here. And so therefore, if you take the reciprocal of that, you get 1 over R1 plus 1 over R2. And now I can compute the partial derivative of that, so dr1. Okay, again, a good Wolfram Alpha use here because this is going to be a bit challenging to find. It's going to require a little bit of work or manipulation, so we'll do this with Wolfram Alpha. And we get, so here's what we get. I have noticed that I have used A in place of R1 and B in place of R2. So the derivative, so if you try to use R1 and R2, it can be a little bit tricky to get Wolfram Alpha to understand exactly what you're asking. So I tend to use different symbols if I need to use subscripts. But the partial derivative comes out to B squared over A plus B squared, which is R2 squared over R1 plus R2 squared. And so if we compute the partial with respect to R2, we're going to get something similar, except this one is going to be R1 over, well, R1 squared over R1 plus R2 squared. And we now have everything we need. We just need to evaluate our partials. So what is dV dy? Well, we know that dV dy is equal to R, and R is equal to one over R1 plus 1 over R2. So now I can actually evaluate what R is, because I'm going to need that. And I'm going to need that because I need to replace all of these symbols here with quantities. So if R is equal to that, then I know that R1 and R2, given in the problem, are 3 and 5. So I will have 1 over 1/3 plus 1/5. And that's going to come out to, let's see, that's going to be 5/15 plus 3/15 is 8/15. And 1 over 8/15 is going to be 15 over 8. And I need that because now I need dV dy. So dV dy is just equal to the value of R, which is 15/8. dV dr is equal to the value of I, which at this given moment in this problem, I is given to us as 2. And so now we should have all the components that we need in order to calculate dV dt as a number. So dV di is equal to 15/8. So I'm going to replace that with 15/8 times di dt. Well, that was given to us in the problem as 0.1 plus dV dr, which is equal to 2 at this instant. dr1, we didn't compute those yet, so let's do those real quick. That's going to, dr1 is going to be R2 squared. And those come out to 25/64 and 9/64. So plugging them into our formula here along with the other unknowns, knowns gives me 0.6 volts per second, which is the rate that we're looking for. And that's our final answer.